good evening, good afternoon, good morning, from which other part of the world you are. Today, welcome to our webinar 56 on Geology, Data and Hazards by Professor Ashutosh. Professor Ashutosh is an assistant professor at Institute of Science, Banaras Hindu University. He obtained his PhD in slope stability from IIT Bombay. He has authored numerous highly cited research articles in engineering and environmental geology, with research spanning slope stability analysis and stabilization, experimental rock mechanics, underground excavation, and machine learning based geotechnical analysis. He currently heads the geoengineering and computing lab at BHU. We are pleased to have you, Professor Ashutosh, on our webinar platform. Over to you.
Thank you, Dr. Rishi, and it's indeed an honor and a pleasure to be among you guys. So I'll commence my presentation. Since most of you are from geotechnical background, or some of you may be from mining background, some of you may be from environmental background, the question that I posit today is how geology, the relevance of data, hazard, risk, how they're intertwined and how we should deal with them. You must have gone through numerous research papers, research articles, which primarily focus on the hazard aspect. Now it's time for us to move beyond the hazard into the risk aspect, because everything is tied to economics. And the number one issue, the number one problem that plagues the rock engineers in the hilly terrain are stability of excavated slopes or cut slopes. So I've named this presentation Geology, Data and Hazards, how one leads to another for something really quantifiable, and specifically in when it comes to rock falls in the Himalayan region. The area that we have taken is in Kinnaur district, Baspa Valley, Himachal Pradesh. So moving on to the next slide. Moving on to the next slide, slide number 2. Yeah, rock falls are different from other types of slope failure. Slope failure is essentially downward and outward movement of a ground which has a gradient, which has a slope. So if it has a slope and the movement is downward and outward under the influence of gravity, that simply signifies instability of slope. Landslide is an umbrella term which takes into consideration all different types of slope failures. Rock falls are a peculiar type of slope failure because they take place in competent rocks. Other slope failures, the general conception is the rock, the soil, the earth, the debris has to be weak. Then the slope will collapse. But for rock falls, you need to have two prerequisites for them to happen. One, the intact rock needs to be competent, as in its compressive strength should be 80 MPa, 120 MPa, more in the affinity of around, let's say, above 50 to 60 MPa, and the slopes need to be steep. So these are the conditions which dictate the phenomena that we call rock fall. Another distinguishing factor for rock fall is that they have a very peculiar falling, rolling, bouncing motion, which is different from other slope stability phenomena. Most of the analysis which has been devised in the last 50 years is for soil slopes and lately for rock slopes, and they consider the movement to take place along a certain plane. Here, the initiation is through that plane. It could be planar, it could be wedge, but the total movement takes into account rolling phenomena, bouncing phenomena. So moving on to the next slide. This is the brief about how rock falls are different from other slopes instability. The study area in which we have endeavored this research is from a very steep Himalayan terrain. It's around 100-120 kilometers from Indo-Tibetan border. The rocks are granitic gneissic. Mostly we have Raksham granite, and the compressive strength ranges around 90 to even 130 megapascal. The elastic modulus is quite high. Poisson's ratio is around 0.21, 0.22. This region, the intact rock is pretty robust, pretty strong. On the contrary, the slopes are also steep. So we have both the ingredients for rock falls to take place. We have competent rocks which are traversed by discontinuities, which are traversed by joint planes, and we have steep slopes. Along with that, these are the two important geological or rather rock engineering criteria which make this region vulnerable to rock falls. Rock falls are recurring in this region. They take place everywhere. Gladly, the amount of rainfall in this region is quite low, but whenever there is rainfall, the instances of slope instability and rock falls, they are increased manifold. Now moving on to the next slide. Yeah, is this is the precursor of this research that we undertook. A tourist bus was passing along Batseri or near the Batseri village in Baspa Valley in July 2021. A rockfall event was triggered that sadly took lives of 9 tourists. So that was the precursor as to why and how. Now, these hazards, they stem from geology. They stem from the ground. But in order to come up with robust decision making, we need data. We need something quantifiable. Now, moving on to the next slide. Yeah, lithologically, as I already mentioned, geologically, these comprise the higher Himalaya, and we have thrust belts, main crystalline thrust in the near vicinity. So, beside the inherent framework of the rocks there, we also have certain amount of seismicity. One thing to be kept in mind is Himalayan rocks are preconditioned to fail structurally. It is not something abrupt. They are already preconditioned because of their genesis and all the tectonic history that they have undergone. They are preconditioned to undergo failure. Our job comes in to assess the type of failure and the population it threats. It puts under threat. A failure in a very remote region where no one is residing is geology. It's a natural phenomena. But if something that affects the population, then we call it a disaster. Moving on to the next slide. Yeah. So what we have endeavored here is to purely come up with data driven, field data driven, which do not rely a lot on geotechnical tests, but purely field data driven approach which can quantify hazard plus risk. So we have field observations, we have structural discontinuities, we quantified them, then we come up with the hazard in that region, then we collate the population, the consequences of what if the hazard takes place, and what will be the consequence if the hazard takes place, let's say in an area A or in an area B. And we have augmented these approaches with core rock engineering tools such as kinematic analysis, which tells us the type of failure, structural failure that may take place, and also rockfall simulation, 2D rockfall simulation, which is essentially a statistical model. In the end, everything has been combined together in a GIS framework to come up with maps for that specific stretch of road in which all the regions or all the specific zones along the road have been mapped according to the risk they pose. Not merely hazard, the risk they pose, which again is tied to the population that they may influence. Now, to the next slide, please. Yeah. So the approach that we have taken is study the geology, then gather all the field data, then we went to rockfall hazard rating. That is essentially it tells us what is the probability of a rockfall hazard in a specific region. Then we went to risk evaluation. We used Missouri rockfall hazard rating system. After that, we did global slope performance index rating because the conventional approaches they tell if a slope is stable or unstable. We needed an approach in which we could know if it's partially stable, if we'll have local bench failure, if we'll have multiple failure, or if we'll have total collapse. Then there was simulation, and in the end, we could come up with this detailed uh, hazard and risk maps for that region, which can surely and would eventually help the planners while designing the mitigation measures. Moving on to the next slide, please. Yeah. So our study started from Raksham, which is close to or northernmost part, and around 23 kilometers south of it lies the village Sangla. So the total stretch that we undertook was 23 kilometers from uh, Chitkul to Sangla, and we divided the slope sections into 19 different distinct zones based on the similarity of you can say lithology or rock character. Or there were some soil slopes too, but that's a different aspect of the study. But these were all rock slopes. What we gathered from the field: slope geometry, discontinuity orientation. As rock engineers would agree with me, failures take place most of our near earth conditions along the joint planes. They have the minimal shear strength, minimal shear resistance, they have minimal or zero cohesion, minimal or zero tensile strength. Their orientation, their roughness, aperture, filling, and also we had taken the rebound values from the joint surfaces. And also a noting was done of what was visible, the predominant mode of failure. Was it planar? Planar being taking place along a single joint plane. Wedge implies that a wedge is being formed through the intersection of joints. And toppling essentially is when you have very steep rock cliffs and joint or rather discontinuity faces dip inward and the blocks topple. Throughout this presentation, I may interchangeably use the terms joints and discontinuity. However, they imply the same thing in this context. They are fracture, defects, or planar features in rocks that make their whole rock mass discontinuous. Now, the next slide, please. Yeah. So the data was gathered, thoroughly gathered. We mapped numerous joints from a single location. All the joints were plotted and density was measured, and we could come up with sets because orientation does change. So we were making sure that we take in the variability in joint orientation, because if you have gone through Goodman's book in block theory, then for structural failure, it's all the interplay between orientation of excavation and the in situ rock. Now, moving on to the next slide. Yeah, again. So as you can see, we were recording different joint planes, different joint characters, and putting them in a set, collating them in a set. The predominantly, moving on to the next slide, please. Predominantly, we found three dominant sets of joints: J1, J2, and J3, dipping in south and southward direction. There were other joints which were non-systematic, and they were also included in the analysis. But predominantly, there were three sets of joints, one of which was the foliation plane. Here you can see the foliation plane being uh, denoted as J1. Yeah. Next slide, please. This is S3. S3 is near Chitkul, as in the northern part of our study area. This is S8, comparatively or relatively southern part of our study area. Yeah. Next, please. Yeah. So as you can see, we could already see massive failures which have taken place in the past. The good thing about Himachal Pradesh is they're pretty proactive when it comes to cleaning the road. So whenever there is debris, it usually gets cleaned rather quickly. Yeah. Next slide, please. Yeah. This is S14. It's near Sangla, and these are the type of rock masses where you can clearly see indication of planar failure. As you can see, the yellow markings, yellow shading, J2, these are the planes along which blocks can fail in a translational manner. Yeah, next please. Again, this is our site 18. It's near Chitkul, and you can clearly see well-defined, well-formed joints. And if you look closely, where you see an intersection of J1 and J2, that is a wedge that is being formed there. Next, please. Yeah. So initially we did kinematic analysis. Kinematic analysis is the most simplistic analysis for rock slopes. It is made for rock slopes, and the test that we do is called Markland test. The assumption is there is no cohesion in the joint plane, and we can ascertain if there is a proclivity of rock mass to fail in a planar manner, in a wedge failure manner, or toppling. So it won't tell you if the failure will take place or not. However, it will let you know about the propensity, the likelihood of the kind of failure that may take place. This is quite crucial when you're designing the mitigation measures. Let's say you're designing for rock bolts, for wire meshes, then this information becomes imperative. So we did the kinetic analysis for all the 18 locations. Now moving on to the next slide. Yeah. So as you can see, the field signatures as well as the kinematic analysis says 80% of the locations have likelihood of wedge failure. 80%. So this 23-kilometer road stretch has 80% likelihood, or the 80% of this 23 kilometer has high likelihood of wedge failure. So what does wedge failure do? It creates open and loose blocks, which eventually snowball into rockfall events. There were instances of planar sliding too, however, they were comparatively low. And there were also signatures of toppling failure. Toppling failure are the biggest, what you can say, precursors of rock falls. Because for a toppling failure to exist, you need to have really steep slope. If it is not steep, then the failure mechanism would change and it won't be a typical rock fall event. Next slide, please. Yeah. So these are the kinematic plots. On your right part of the screen is S1 and Chitkul village, and on the left part of the screen is Sangla village. And the kinematic analysis just plots planar surfaces. So it will plot the joint plane in a great circle. It will plot the slope surface, and using the friction circle, we can ascertain the likelihood of failure. I'll repeat again, it won't tell if the failure will take place or not. It will tell you the propensity, that what is the likelihood of a specific type of failure to take place or not. Again, moving on to the next slide, please. Yeah. So for all the 19 locations, you can see the most prominent failure pattern that was recorded as well as observed was wedge failure, which implies that intersecting joints were leading to creation of loose blocks, intersection of joints. Then there were instances of toppling failure and some amount of planar failure. The point that I'm trying to make here is wedge failure was the most prominent one, and it is the biggest precursor for mega rockfall events. Yeah. Next slide, please. Yeah. Now we move to our next task. How do we quantify the rockfall hazard? Now, this is a hazard quantification tool rather than a core geotechnical tool. It's a hazard quantification tool, and it was given by Pearson in 1991. So, rockfall hazard is essentially a function of the slope condition. Slope condition includes the type of rock, the type of discontinuities, the weathering grade, the strength of it, the stresses acting on it, and combined with rockfall frequency. How frequently do they take place? Are they frequent? Are they not? Then these two information that combined with traffic exposure. Do you have a lot of vehicular traffic or is there none? When you combine all these informations, you come up with a number, a rating system. It is exponential in nature. Exponential in nature, as in the rating has been devised to be exponential in nature. So anything above 400 is considered high hazard for rockfall. Anything above 700 needs to be avoided at any cost. Yeah, next slide, please. So I won't go into the nuances of this, how we rate things, because uh, it's essentially you take the observations, concrete, tangible observation, and you map them according to different parameters which have been listed. So yes, if it's more than 400, that means it is it poses high hazard, rockfall hazard. This is this scheme is quantifying the hazard. There is traffic exposure, but essentially we're not talking about the core risk aspects. The design of RHRS has been such that it is quantifying the hazard aspect. Yeah. Next slide, please. Yeah. So we have collated all the data and we have done IDW interpolation, which the underlying philosophy being if 2 points are close to each other, they would have similar traits, be it lithology, be it the stress regime. So we have uh, used IDW interpolation scheme to create these maps of the distance of sight, which is one of the parameters. If you have high sight distance, as in you have more maneuverability, when you have average vehicular risk, how many vehicles are crossing a certain cross section. Then we also have this interpolation map of block size. Larger the block size, larger the vehicle it can affect. Smaller the block size, the effect on it hitting a vehicle would be rather low. And then also the block friction. The block friction that we had calculated, we had also brought samples from the field, and we had used Barton's joint roughness coefficient for block friction. Next, please. Yeah. And we also retrieved 2011 population census data, and we also used that interpolation method to create the population density map of the region. how many residents are residing along this study stretch. So the red mark that you're seeing, that is Batseri village, and in the right in the middle that you're seeing the yellow zone, that is Raksham village. Population near Chitkul, the right corner, is quite low. It's mostly inhabited by ITBP. Next, please. Yeah. So after collating all the data, we produce these maps, which are essentially the GIS component that we have used is the uh, interpolation method. Otherwise, all the information steps from actual data as in be it geology, be it, we had literally counted the number of vehicles for that specific spots, the number of vehicles passing through. Eventually, we could come up with the RHRS hazard map of the region. Now, another thing to be kept in mind is the hazard ratings, they follow different schemes. We have used min-max scaling of our hazard rating to rescale our hazard from 0 to 100. So this is essentially uh, good for comparison. However, the actual values, they vary from what the actual hazard rating was. So as you can see, the maximum hazard is posed near Raksham, near Batseri, and in a vicinity where the rockfall events were persistent near Chitkul. Next, please. Yeah. Uh, so the rockfall hazard map was created. We included the data, the vehicular, the side distance, that, and we used interpolation. Now we move towards what is the risk factor here. As you are aware, risk is equal to hazard times vulnerability. And in all the economic models, the risk index, this is what matters when we are designing for something or planning for something. So risk is probability of rockfall plus the consequences. A massive rockfall may take place, but there is no settlement, no traffic. It will pose low consequence. On the contrary, you may have a rockfall which is very small in scale, but it's near a settlement. So the consequences would be quite high. That is how we devise the risk factor. So again, if you think about it, the risk is combining the geology, the geotechnology, and how people live. When you're combining these three aspects, you can come up with risk. So it has 23 parameters, uh, and they were comprehensively noted in the field. And the scale is comparatively goes from 0 to 100, uh, contrary to the previous RHRS Rockfall Hazard Rating System scheme, which can go beyond 700 as well. Yeah, next slide, please. Yeah. So we did the hazard zonation, and we found that 11% of our 23-kilometer stretch was very high risk. I'm not using the word hazard, I'm using the word risk. It was high risk, as in even a small rockfall event in that region could lead to disastrous consequences. And 21% was high risk. This has been collated with all the geological, geotechnical data and the population data. And as you can see, zones where we have higher settlement, higher population, which are S18, 19, 13, 11, and 8, are they fall in high risk zones, and the sporadic S9, S15, S16, which are highest consequences, because here the larger contributor in the multiplying effect was uh, the Population density. Site S15 and 16, they were near Batseri village. Batseri village. Also, 90% of the population in this valley resides in high risk and high consequences zones. This is worrying, and there have been instances of fatalities in the past. And this work actually substantiates that how vulnerable that population is. Moving on to the next slide, please. Yeah. So, as with the previous case, we had created a rockfall hazard rating scheme. Here we have created a risk map, and in the zones in violet uh, colors are comparatively low risk, and the zones in greener colors are high risk. And most of the high risk, high consequences zones are near settlements, near villages. Now, the consequences also include the economic aspect in this study. So, there are regions where we have a lot of apple orchards. So, they have also been considered in this risk calculation. And this map has been created again through interpolation of weighted average. There are different kriging and interpolation techniques, but we stuck with the most simpler and intuitive one. We wanted it to be intuitive. That is why we undertook this. Next slide, please. Yeah. So this is the final map, the risk map, and you can see the southern portion on the left of your screen, where large number of population resides, is eventually more prone to rockfall risk. Next, please. Yeah, this is the consequence map. The greener portion will have higher consequences. As you can see, S11, S9, S10, near S, these certain regions, you have high amount of apple orchards. There are residing populations in S11 and S9. You have Raksham village, but since we have also taken into consideration different attributes of the consequences, you can see the distribution of consequences does not exactly tally with the uh, rockfall risk map. Please, can you move back to the previous image? Previous image, sir. Yeah. See, it is the rockfall risk map. Next slide, please. Yeah, this is the consequence map. So they may look similar, but if you look closely, they are not exactly similar. Can you go back to the previous slide, please? This one and the next one, please. Yeah. So this one is giving you the rockfall risk, and this one is giving you the consequences. Which regions will face higher consequences? Next, please. Next slide. Yeah. So again, this Missouri rockfall hazard rating system gives us how we can map low risk, low consequences, high risk, high consequences, low risk, high consequences, high risk, low consequences zones. And based on our calculations, you can see most of the, although they are in the lower extremity of that high risk, high consequence quadrant, albeit they are in the lower extremity, but they are in the high risk, high consequence quadrant. Yeah, next please. Yeah. Also, we have plotted population distribution with rockfall hazard rating and Missouri rockfall hazard rating system. And you can see where population is high, then both RHRS and MORFH are in concordance. As in, if you look closely, where there is, yeah, someone has his or her mic on, please. Yeah, as you can see, yeah, Mr. Gulam, please switch off your mic. Okay, so uh,
Saurav, can you switch off his mic?
yeah, so this is what we call a spider map. It's just a fancy name and a different way of visualization where you can compare three variables in a way. So wherever there is high population, you can see good coherence between rockfall hazard and rockfall risk through different approaches. Now, the point that I'm trying to make here is the geological hazard is essentially a socio-economic hazard. These hazards, as of 2026, are socio-geological economic hazards, and you can see the distribution of high risk zones are near the high population zones, which also is in conformity with rockfall hazard rating system, which essentially shows the likelihood of rockfall events. So these three approaches, or rather say, if you add the kinematic analysis to three approaches, are in good conformity with the population data, with the past events, and the rating systems which have been incorporated in this research. Next slide, please. Yeah. Now, you must be aware of rock mass rating, Q system, geological strength index. Like Barton, he is strictly against geological strength index. Rock science and a lot of their people truly love geological strength index. We have employed Global Slope Performance Index, which was given by Sullivan in 2033. He had actually designed this for mining slopes. The reason we employed GSPI is we can get a very fair idea of slope performance when we can expect localized failures and when we can expect total collapse. So this is one thing we wanted our emphasis on, and the parameters that it takes is rock strength, UCS, rock character, structure, orientation, and water. And uh, unlike Q system or RMR or SMR, its value ranges between 5 to 25. So higher the score, that means the slope is it is likelihood of collapse is much higher. Next, please. Yeah. So uh, multiple bench failures. That means in totality, the slope won't fail. You won't have the propensity for its whole collapse. But because of the orientation, you'll have multiple bench failures. And it was noticed and it was discerned for 8 locations. Then also on a local bench failures, it was found for 7 scales, as in the slope failures localized. And these are good triggering points for rock falls. Now, there was one slope near Sangla which was quite weathered, which did have the propensity for a complete failure. So there were multiple bench failures which were noticed as well as verified through GSPI, then local bench failures, and a very minuscule for complete failure. Next slide, please. Yeah. So these are the locations, and you can see uh, the blue one denotes. This is a bar plot. The blue one denotes multiple bench failure, which you can see in location S3, S4, S5, S6, and furthermore. Then you have local bench failure, which is dark green in color. For light brown color, you have widespread movement. That means these locations or in the vicinity, you also had some colluvium, some debris, which uh, showed signatures of failures, and location S18 did show failure. Next, please. Yeah. Okay. Then we also did 2D simulation because merely telling people that the rockfall will take place or you are at high risk won't do. We eventually need to devise uh, mitigation measures, robust mitigation measures, which could be implemented at locations which are high risk and high consequences. That is why we did 2D simulation. Uh, Three assumptions that we undertook was we took a uniform mass of 1000 kg. Uh, and another thing is it was a rigid body simulation, so there was no dampening after the impact. So these were some assumptions, or rather the lacuna in the simulation. We did it for all the 18 locations, and our end goal was to find the appropriate kinetic energy because your rockfall barriers need the maximum kinetic energy and maximum bounce height output for their appropriate and uh, long-term design. Next slide, please. Yeah. So most of the locations near Sangla, as in near the southern end of our study area, showed energies which are higher than 1000 kilojoule, which can create or which can cause major damage. Major damage. And bounce height usually exceeds 5 meters at certain locations. Now, run out distance, it went up to 900 meters. This is purely derived from the slope geometry. The slopes are really steep. Higher Himalaya is steep. Next, please. Yeah. So this is a screen grab of the simulation. We put in the properties of bedrock, talus, and road. The black portion that you're seeing is the road. So the restitution values were used as per the material there. Next, please. This is for S5. Next slide, please. Yeah, this is for X6. Next slide, please. Yeah, S11. This is Batseri. As you can see, it's pretty steep and the runout distance is quite high. Next, please. Yeah, this is near Sangla. Next, please. Yeah. So if you'll ask me what are the key findings of this work, uh, as was my opening statement, Himalayan rocks, they are preconditioned, they are predisposed to undergo structural failure. So it should never be a surprise for us that they'll fail. On the contrary, we need to work on how to assuage the damage, how to minimize the damage. And hazard is geology. But for actionable designs, for actionable mitigation measures, you need quantifiable data. You need to put reliable numbers to those observations in order to have something actionable, something that you can eventually use in your design. And rockfall threat is there. There is documented proof of that. Locations are vulnerable. Now, the mitigation measures should keep in mind where the hazard is and where the risk is and what are the consequences if we don't comply by them. Next slide, please. So if you'll ask me what are the key lessons from this work, uh, Himalayan roads are a geotechnical experiment. Whenever you are excavating, you are redistributing the stresses. So those changes would counteract, would modify uh, the surrounding stress regime would lead to relaxation, stress relaxation, and would undergo weathering and would eventually undergo failure. And hazard in Himalaya, hazard always exists. How we deal with it or how we prepare for it defines the disaster that we face or we save ourselves from it. And the more data you have, it will reduce the subjectivity. It will strengthen your decision making when it comes to design or stabilization measures. And most of the disasters, they are defined by the population they're being exposed to. Another thing, we have used two different hazard rating systems. In my opinion, more should be used because any method, any scheme relies on certain assumptions. The famous statistician once said that all the models are wrong because they all have certain assumptions. So, irrespective of how much faith you have in your model, in your simulation, keep in mind that it has some underlying assumptions. Nature does not follow simple rules. Nature is complex. So, multi method assessment is the way to go ahead, way to proceed. Next slide, please. Yeah, so these research findings were published in the Bulletin of Engineering, Geology and Environment. And if you have any query in future, you can write to me at ashutosh.geo@bhu.ac.in or WhatsApp at 7060107146. Thank you for your time and patience. Thank you.
So,
Now I welcome questions. Any question? Just speak your mind, please.
yeah, thank you, Ashutosh, for this insightful and informative presentation. I believe everyone is grasping all the knowledge. From my behalf, I will ask the question: like, is this model conceptually or quantitatively differentiate between a rockfall sources zone or transit zone or like deposition zone? Is model does that?
No, essentially, it takes into account the initiation points. And as far as deposition is concerned, most of these are designed for road safeties. These are designed for road safeties. So they are mostly taking into account the geological considerations along the excavated slope.
Okay, thanks. The next question is from Patil Harshvardhan. What was the rock mass volume which observed at Sangla location and considered in rockfall simulation?
Okay, rock again. In this simulation, the input that we use is measured in terms of mass. So mass and the dimensions of the block, the ratio of the block. We don't directly use the volume per se. We use the mass. So the mass was 1000 kg. This is the stochastic simulation method. It is, I say, as I've mentioned, it has that assumption that there's no damping, and the core value that it takes into account is the mass. So for a specific density, you have to re-engineer to get the volume from the mass.
Yeah. The next question from myself. So, you have these static data set for with you, but do
Mhm.
you find any limitation like because the rockfall is the dynamic process?
Mhm.
So is there any
I find I find many limitations. I find many limitations. The first one is uh, the coefficient of restitution. We always have to like back analyze it to get the appropriate value, because the experimental setup to get the coefficient, actual coefficient of restitution value, is tedious, time consuming. That is the first one. The second one is the dampening effect, because if I want to ascertain the block height, I need to know what is the dampening effect due to vegetation, due to talus. So I think I already stated that these models underlie a lot of assumptions. I think a better approach can be doing these in distinct element modeling, UDEC, but you won't get the runout distance there. Because rockfall simulation, 2D rockfall simulation is essentially a statistical simulation. It is not a numerical simulation. Yes, so there are a lot of assumptions, and I think if future rock engineers should really focus on rockfalls, because the more highways that we're creating, the more rockfall avenues we are generating. And the region where we work, this region undergoes immense freeze and thaw cycles. So the rockfall was initiating at a height of, let's say, 5,000, 4,000 meters above mean sea level, because frost action was taking place. During the night, there was freezing, and morning there was thawing of the ice, which was leading to generation, this fragmentation of large blocks, which by even the mildest triggers would create large rockfall events. Yes.
Great to hear, Professor.
Yeah.
I believe there is no more question. I will ask from my side again. The last one, like
Okay.
which input parameters show the highest sensitivity in the model?
Which model?
Yeah, which input parameter shows the
No,
highest
which model are you talking about? Like hazard rating system or like simulation or what?
the hazard one?
Okay. They have been given different weightages, but again, the most prominent one is geological structures. If you come to consequences, the vehicular traffic. What is the vehicular traffic? If you witness 60 vehicles in an hour, or if you witness 5 vehicles in an hour, we literally counted the number of vehicles passing through a specific section for different scenarios or for different sections that we undertook. So sensitivity, if I'll give you broader view, generic view, the geotechnical aspects of the slope, they are the primarily driving factors when it comes to hazard, and the proximity to population. They are the primary or which influence the model most when it comes to risk and consequences. And if you dig down deeper, what in geology? Then in geology, the structural orientation. Are the joint planes, are they dipping towards the valley or dipping inside? The work done by Goodman and Shih in the key block theory, it's marvelous and dwells much deeper into how geometry gives the degree of freedom to blocks, and which in turn dictate the blocks if they'll fail or not. So yes.
Yeah, that's it from my side. Yeah, thank you, Professor
Any
Doctor,
question? Okay.
for this excellent session filled with valuable insights and these practical takeaways.
Okay, next time we can make it more technical. And thank you, Rishi, for inviting me. It's wonderful, and I also checked out your YouTube channel. This is a great step forward as far as the dispersal of knowledge is concerned. Because the thing is, practitioners, the rock engineer, geotechnical practitioners, they don't often meet. They don't often talk. If they talk, they mostly talk about all the clerical things, contractors like this and that and that. But the avenue that you have created and bringing in people from the industry, the practitioners, It is. I'm pretty sure it will bear good fruits in future.
Thank you. Thank you very much for your kind words, Professor.
So, are we done for the day?
Yeah.
Thank you, Ashutosh sir. Thank you so much.
Thank you, thank you. Don't call me sir. You can just call me Ashutosh. I may look
I
old,
would
but
like
I'm not that old.
to I would like to ask something because it
Yes,
was
sir. Sure,
a
sure, sure.
purely rockfall topic. So
Yes,
imagine
sir.
if there is a huge cover of soil over rock,
Hmm.
and rocks are very fragile, means they are weathered and supposed to be get like residual soil. Then how we are working in it? Because I am very new in tunneling. I have just completed my MTech degree at the age of 48,
Hmm.
and it's a
Congratulations,
new
sir. You
subject.
are an inspiration. You are an inspiration for us.
So I am trying to learn all these things. So I am working in this industry in geotechnical field as an associate geologist for 20 years. But really, it was nice, interesting, very interesting session with you. So next time, whenever it will come, also make something for soil because you saw a lot of landslides and everywhere there was a rock cut slope. So when there is open rock, we can geologically map it. But when the rock is under cover and it's not quite possible to map it and to predict how it will fall during, as you said, rainfall, then how
Yes,
we
sir.
will tackle these things.
Yes, sir. I totally get your question. Uh, when you're talking about underground excavation, then portals and intersections, they are the most vulnerable portions in vulnerable components in an underground excavation. Mostly, if you have debris, I think I can call it debris, or should I call it earth, soil?
Yeah, it
Shantanu,
can be a debris better.
okay, okay. So depending on the thickness, mostly if it is near the portal, it has to be removed. Because what happens is if there is slight introduction of water, let's talk about water first. Then you'll end up having is debris flow or mud flow. And now what you're saying is you have a debris which is overlying weak rocks, isn't it? Debris underlying weak
Yes.
rocks. Yes. So in that case, the stabilization has to be designed for the weaker rocks. It also depends on the thickness because removal of soil is much easier than removal of rocks. In underground excavation economy plus geotechnology, it dictates the decision. For slope stability, if it is weak, then the probability of failure is always there. Rocks can be stable, can be meta stable, but if you disturb soil, it will fail. Especially if you are, uh, is it near the portal or near the edit or where this soil and rock?
No, actually, it was just my general question. When our rock is covered,
Okay, okay, okay. I sorry, I got your question now, sir. In that case, what we do
see,
is
when
yes.
you saw slides where rock was stabilized or supposed to be stabilized, but in those areas like Himachal where there is natural landslide, where there is a huge flow and we don't know what type of rock beneath the soil because maybe it's a clay silt or whatever, then how to work for tunnel alignment, that I was
Okay,
trying
sir.
to ask.
Then first of all, you need to use geophysical
Because it
methods
is
or
hidden, it
drilling.
is hidden.
Yeah, yeah, yeah. You have to use geophysical or drilling to get the depth of in situ rock. And for those type of
Okay.
slopes, we usually, if they are debris, then we'll most likely put gabion walls there. And if they are finer earth, then we'll go for retaining walls, where there is no visible
Okay.
rock and the slope is mostly earth and debris. Then the treatment becomes different, entirely different. Yeah,
Okay.
and
Okay.
again, in order to design, you need to know the depth of in situ rock. So you'll have to do some thorough subsurface investigations.
Okay. Thank you. Thank you so much. Thank you.
My pleasure. My pleasure. Any more
Yeah.
questions?
If there is no one, or maybe you already had shared your email ID, so they can reach out to you.
Yes, yes. Okay, there is. Okay, okay, okay. I think I've answered the. Yeah.
Yeah, that's why I didn't. Yeah.
Mm,
So before we conclude, I would like to remind you everyone like to stay connected with TAIym through our social media platforms and website for updates on upcoming webinars. This webinar also be uploaded on YouTube shortly after due diligence. Our next session will be announced shortly, and we look forward to your continued participation. Thank you all. Thank you, Dr. Professor Ashutosh, and every participants who joined. Thank you once again, and have a great evening ahead. Yeah.
Thank,
thank
Stay
you.
safe. Have a good day.
Goodbye.
thank,
Bye,
Yeah.
bye.
bye.